Hi folks, today we're going to be talking about the mole, one of the coolest units in chemistry. You were asked to come up with a way to figure out how many jelly beans are in the jelly bean container, right? The idea is to think about how you could actually get all of those jelly beans counted without actually being allowed to count them all. So I'm hoping that one of the ways that you thought of possibly doing it was looking at it from the standpoint of mass. Now, granted, not all the jelly beans are exactly the same mass. However, they are relatively close to each other, so you could potentially get very close to that. So here's the question, all right? What if I asked you to get me a single atom of copper? Is that possible? As you can see, there's a big old fat no. Is it possible for you to get that? And the reason being is that isolating a single atom is too difficult because of its size. That's the biggest issue. So atoms, ladies and gentlemen, are ridiculously small and too numerous to count. And to give you an idea of their size, I mean, they're 50 to 150 picometers. And you're like, what the heck is a picometer? Well, if you imagine taking a meter, okay, and then taking just a millimeter and dividing it by 1,000. So imagine a millimeter, okay, about yay, and then taking that millimeter and dividing it by 1,000. That would be 1 micrometer then. Each one would represent a micrometer. Now take a micrometer and cut that into 1,000 segments. Now you have a nanometer. And if you take a nanometer and cut that into 1,000 segments, now you have a picometer. So we're talking about something that is ridiculously small. So the idea is, how is it that you're able to count all of these? How is it that it is even possible? So because of its size, it's next to near impossible for you to actually be able to count them all. And so I've got an image there. So imagine if the nucleus of an atom was the size of a grape seed. All right, now for those of you who don't know what a grape seed is, there are actually grapes that contain seeds. And so if you get one of those seeds, put it on the 50-yard line of a football field. Oh, wait, sorry, this is San Diego Academy. We don't understand football because we don't have that. So imagine if we put that in the center of our field. Roughly, if we were to go to, for example, something like Qualcomm Stadium, or sorry, San Diego Credit Union Stadium now. If you go there and you put the grape seed on the center of the 50-yard line, the size of the atom itself would extend beyond and towards the parking lot. Okay, so it's a bunch, again, remember, empty space, kind of like my head sometimes. So atoms and molecules and ions, okay, we need to be able to get a tangible amount, okay, meaning I can't count them all. There's no way I can isolate one. So how do we know how many we actually have? And so there was a scientist who decided to come up with a way of being able to actually count without counting. And so what he came up with the idea is that a mole, okay, a mole, by the way, is derived from the Greek meaning heap or pile, okay? So a mole is, by definition, the amount of a substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. Now you're going to say, well, how many particles are we talking about? I mean, if we got 12 grams of carbon-12, what, what would that be? Well, they isolated and figured that out to be 6.0221415 times 10 to the 23rd. Atoms, that is, of the carbon-12. Which, in all intents and purposes in this class, we're going to use 6 times 10 to the 23rd. So what that means is that 1 mole is equal to 6 times 10 to the 23rd. I mean, a mole of anything is equal to 6 times 10 to the 23rd. Okay? So this name, the name of the number is given as Avogadro, not avocado, Avogadro, okay? You don't get to choose your name. So Amadeo Avogadro. And so we call this typically Avogadro's number, okay? And what this allows us to do is it allows us to count, for example, atoms, ions, molecules, or formula units without actually having to count them because it's next to near impossible. So I've got a short little video I'd like us to watch, so give me a second to get that playing.
Avogadro's number is 6 times 10 to the 23rd. Any collection of this many objects of any kind is called a mole. In general, We use Avogadro's number to convert numbers of atoms into measurable amounts of chemicals. Avogadro's number is really big. If we covered the lower 48 states with a mole of popcorn, or 6 times 10 to the 23rd pieces of popcorn, the pile of popcorn would be 500 kilometers deep. The layer of popcorn would be twice as high as the International Space Station. But an equal number of atoms of magnesium can fit on this scale and weigh only 24.3 grams.
So ladies and gentlemen, I just want to point this out. If we think about that, that's a ridiculous amount of popcorn, first off. Who needs a mole of popcorn? But the idea that I can have a mole of magnesium, meaning 6 times 10 to the 23 atoms of magnesium sitting on a balance that has a specific mass, this is a way in which we can count without having to count. Okay? So I got a quick other little video I want you to watch.
A mole is a quantity similar to a dozen. There are 12 items in a dozen, and 6.022 times 10 to the 23rd items in a mole. A dozen eggs, a dozen bagels, and a dozen pencils have different weights or masses and have different properties. The term dozen tells you that there are 12 of the item. Similarly, a mole of iron and a mole of copper have different masses and have different properties, but both represent the same number of atoms, 6.022 times 10 to the 23rd atoms.
So if we look at this last image that they show us, they're giving us the idea that we have iron on one side and copper on the other, okay? Now, the iron, ladies and gentlemen, has a different mass than the copper. However, each one represents, and here's the key thing, it represents a mole, meaning that there are 6 times 10 to the 23rd atoms of iron there present on the balance, and 6 times 10 to the 23rd atoms of copper there in the balance. The thing that differs is their masses. That's the key. The mass is the key to being able to count. Now, how is it that we can even do this? So that's what we're going to be examining as we move through. The other thing I want to point out, if you notice in the very beginning of that little clip, they talked about the idea of a dozen. Well, who doesn't know what a dozen? A dozen means 12, right? That could be 12 of anything. It could be 12 pencils. It can be 12 glasses. It could be 12 of me. That would be awful. But the idea is that a dozen just means 12, just like a mole means 6 times 10 to the 23rd power, meaning that's how much is in a mole. So if I had a mole of, I don't know, sunglasses, then gosh, I'd have a lot of sunglasses, wouldn't I? A ridiculous amount. So again, think of it as like a dozen. A dozen of anything means 12. So if you have a dozen pencils, you would have 12 pencils, okay? So what if you have a mole of pencils? 6 times 10 to the 23 pencils. That's a lot of pencils, okay? So therefore, 1 mole of anything is 6 times 10 to the 23rd. So what are we going to do with this number? What are we going to use it for? Well, we're going to use it by what is referred to as the molar mass. This is what allows us to count without counting. So you're going to probably want to have a periodic table out in front of you in order to make this easier, or you can just follow along with the presentation here, okay? So what we're going to be looking at is the idea of looking at kind of an alternative definition. So the alternative definition of a mole is the amount of substance that contains Avogadro's number, 6 times 10 to the 23rd. So what we can say is this: the atomic mass of the element is equal to 1 mole of the substance. Let me repeat that one more time. The atomic mass of the substance is equal to 1 mole of the substance. So if we have, for example, a periodic table in front of us, and we were to look and examine it, I could actually, for example, pick out something like silicon, and I can say, oh, its atomic mass is 28.09, which means that if I wanted to go get a mole of silicon, I would go get 28.09 grams of it. So if I wanted 1 mole of silicon, and yes, to abbreviate mole, it's M-O-L. Yeah, just drop the E, okay? I would go get 28.09 grams of it. That's it. What if I wanted to go get a mole of iodine? Well, 1 mole of iodine, I would go get 126.90 grams. Now, why is it that 1 mole of silicon has a mass of 28.09 grams and 1 mole of iodine has 126.90 grams? Do they have a different number of protons and neutrons in them? They do. And because we've taken the average mass of them, we're getting the average amount of them overall. Okay, remember there are different isotopes, and this atomic mass takes into account the different isotopic masses that we have there. Okay, so we're going to use this to be able to count without counting, because remember, 1 mole of anything is equal to 6 times 10 to the 23rd. So if I say that this is 1 mole of silicon, that is 6 times 10 to the 23rd atoms of silicon, which has a mass of 28.09 grams. So they're connected. Okay. So here's what we're going to do in our class. We are going to round our molar masses to the nearest whole number. So what I'm going to do is I'm going to pick on an element, and in particular we need to look at an element. I've got a periodic table here, so you don't need to have one in front of you, but we're going to pick on a particular substance. So we're going to pick on arsenic. Okay, everyone got that? We're going to pick on arsenic. So find arsenic on our periodic table. You will see it right here as element 33. And when you look, I want you to find the atomic mass, and you find the atomic mass, and you find it to be, it has a mass of 74.92, okay? That's the atomic mass. So what I want you to do is, first off, round it. So when we round that, and we want to round it to the nearest whole number, I'm hoping you get 75. And we want to add the appropriate units. So the units for this would be 75 grams per mole. 75 grams per mole, and this is 75 grams per mole of arsenic. Okay, so 75 grams of arsenic for every 1 mole of arsenic. Okay, so let's figure out how it is that we can use this, okay, to our advantage. Well, but wait a second. We just looked at it from a single element. What if we have, which most things are, as compounds? What do you think we would do? If you said, hey, we look in the periodic table and we find the mass of each one of them and add them up, you got it right. So if we look right here, we've got calcium, which if you look on a periodic table has a molar mass of 40 grams per mole. And I'm hoping you recognize that there is only 1 calcium here, okay? Then we need to find for sulfur, we find its molar mass to be 32 grams per mole, which there's only 1 of them. But the oxygen, there are a total of 4 oxygens. So that is why I have a 4 here. And so what we do is we simply just add them together. And this, ladies and gentlemen, is the molar mass of calcium sulfate. Now, the only thing you need in order to do this, the only thing that you need to have present in your possession is a periodic table of elements, okay? And you will notice that I will be referencing the periodic table of elements quite often, and I'm going to abbreviate it from here on out as PTE, periodic table of elements, okay? So let's do one more. All right, so I highly suggest that you pause the video and get yourself a periodic table if you don't have one. But here's what we're going to do. Oh, well, I just flat out gave you the answer. It was going to be your turn to try, but hey, we're just going to go with it. It's asked, what's the molar mass of carbon dioxide, CO2? What I'm doing right now, breathing out and talking to you. So if we look right there, I've got 1 carbon, I have 2 oxygen, and I find their molar masses. The question is, where did I get these from? I got these values from the periodic table of elements, ladies and gentlemen. And then what I do is I add these values together and I get the molar mass. So this is the molar mass of carbon dioxide. So what this means is that if I wanted to go get 1 mole, okay, 1 mole of carbon dioxide, I would go get 44 grams of carbon dioxide. What if I wanted to get 2 moles of carbon dioxide? What do you think I would have to do? If you said double it and get 88 grams of carbon dioxide, well, gosh darn it, you're right. What if I wanted to only get myself a half a mole of carbon dioxide? And you're like, can you get a half a mole? Well, all we're doing is getting half the molecules. So yeah, I would only get 22 grams of carbon dioxide. So I'm hoping you're recognizing that there's a connection between these numbers. Now, if I asked you to get me a mole of carbon dioxide, it is totally possible for you to get me 44 grams of it. But it is impossible for you to get me 1 molecule of carbon dioxide. So again, remember, this 1 mole means that I have in my possession 6 times 10 to the 23rd, and that would be molecules of CO2. If I have 2 moles, that would be 2 times the 6 times 10 to the 23rd, and that would be molecules of CO2. Ooh, I'm running all over the page here. Okay, so keep that in mind as we're going through. So I'm going to show you what we can do with this and how we can calculate some stuff with it. Okay, so a lot of times what we're going to be asked to do is convert from mass to mole or mole to mass. So we're going to start with mass to mole. Okay, to help you out, what I've got is this little, what I call the mole map. Okay, this is my mole map. All right, and so what I'm going to be doing is constantly referencing this particular map in order to help us go from mass to mole or mole to mass, okay? But I'm hoping you recognize right at this moment that in the center, right in the dead center, you will notice that there is the mole, okay? And on the outside, we have mass, and on the other side, we'll have representative particles. When we get there, we'll talk about that. But mass, ladies and gentlemen, since this has to do with mass and moles, the mass itself, ladies and gentlemen, is in the unit of grams, okay? And in order to convert from mass to mole or mole to mass, I need the, ladies and gentlemen, wait for it, the molar mass. And where do we get our molar mass from? I'm hoping you're saying, oh, we can look it up and figure it out and add it all up and get it from the periodic table of elements. So let's see what I'm talking about here. So it says, if you have 116 grams of sodium chloride, the formula is NaCl, how many moles would be present? Okay, so first off, right off the bat, what are we given? We are given 116 grams of sodium chloride. That's what we're starting with. And it's asking how many moles? That's the big question. How many moles would be present? So we have to start right here, 116 grams of sodium chloride. That's what we're starting with, 116 grams of sodium chloride, okay? And in order to convert grams into moles, wait, I'm going to go back and look at our mole map. We're starting there at mass, and we want to get to mole. Ooh, I'm erasing. I don't want to erase. There we go. I want to go from grams to moles. That means I need the molar mass. Bust out your periodic tables. Find your periodic tables. And what I want you to do is on your periodic table right now, find sodium. Okay, and I'm hoping you recognize for sodium, its mass, there's only one of them. Okay, and its mass is 35, or sorry, not 35 grams, 23 grams. 23 grams. Okay, and then for chlorine, you have one of them, and it is at 35 grams. So when we add those up, I got 23 grams, I got 53 grams. That, ladies and gentlemen, has a molar mass of 58 grams for every mole for sodium chloride. Okay, so let's check it out. Let me show you how we're going to set this up. We're going to use this thing. This is called dimensional analysis. This is where we show how units go away. Okay, and this is an important math skill in this class that you're going to need to learn. So here it goes. Are we ready? All right, so right here, ladies and gentlemen, is our molar mass. Okay, for every 1 mole of sodium chloride, 58 grams. I know that some of you are looking at this going, wait. For every 1 mole, there's 58 grams. We have 116 grams. If I take 58 and I multiply it by 2, I get 116, so we must have 2 moles. And if you say that, you are correct. but we need to show that mathematically. So our first thing first, we've got our 116 grams of sodium chloride. We're going to put that over 1 because this is in the numerator right here, ladies and gentlemen, and the 1 is in the denominator. Unit analysis, the idea is to get rid of one unit and replace it with another. The unit we want to get rid of is always located in the denominator. We want to get rid of the grams of sodium chloride, and I want to convert it because it's asking how many moles of sodium chloride. So I want to convert it into moles of sodium chloride. Based upon what I have here, ladies and gentlemen, all right, what was given and what we figured out here with our molar mass, there are 58 grams of sodium chloride for every 1 mole of sodium chloride. What's going to happen? Our grams of sodium chloride are going to cancel out. And you're going to say, well, how do they why? The grams of sodium chloride is in the numerator. The grams of sodium chloride is in the denominator. So if we divide the two, gram divided by gram equals 1. So that's how we call it canceling. Okay, so if we do the math here, we take 116 grams of NaCl, okay, 1 mole of NaCl divided by 58 grams of NaCl. Grams of NaCl cancel out, so it's going to be 116 times 1 divided by 58, which, by the way, ladies and gentlemen, comes out to be 2 moles of NaCl. That's how we get. So in 116 grams of sodium chloride, there are 2 moles of sodium chloride. That's one. We got a couple more to do. We're going to go the opposite way here. Okay, in this particular one, we're going to go from moles to mass. Okay, we're going to go from moles to mass. So from here to this direction, we're doing the opposite. But here's the thing, we still need the molar mass, and we get that molar mass from the periodic table of elements, ladies and gentlemen. Okay, so let's take a look at our next example. It says if you have 4 moles of sodium chloride, how many grams would be present? How many grams? So 4 moles of sodium chloride is what we're starting with. How many grams? That's the big question mark of sodium chloride are present there. So let's take a look. Let's figure this out. 4 moles of sodium chloride. Okay. Now, here's the thing. Here's what we got to remember. We've already figured out the molar mass of sodium chloride. The molar mass of sodium chloride is 58 grams of sodium chloride for every 1 mole of sodium chloride. So we're going to set up our math here. This is over 1. The unit we want to get rid of is always going in the denominator. So we're going to put our moles of sodium chloride down here in the denominator, and we're going to put the grams of sodium chloride in the numerator this time. Now, according to what I have here, for every 1 mole of sodium chloride, I will have 58 grams of sodium chloride. So when I do the math here, all right, the moles of sodium chloride will cancel out. I'm going to take 4 times 58. So if I do the math there, I think that comes out to be 232. Check me. All right, and my units will be left as grams of sodium chloride. Now, if you, just for funsies, want to compare this with what we did here, I'm hoping you recognize that these are just the reciprocal right here. This right here, ladies and gentlemen, is the reciprocal of what we did in the previous question. Okay, so just keep that in mind. All right. So we got another one. We've ignored part of our little mole map here. And so what we're going to be looking at is converting moles to representative particles. Now, you're going to say, what's a representative particle? What do you mean by a representative particle? Okay, representative particle can be the following. An atom, an ion, a molecule, yes, me too can spell, and a formula unit, which a lot of times I will abbreviate as an FU, okay? FU, so I don't have to write formula unit. No, there's no abbreviation for molecule, atom, or ion, okay? So these are the smallest parts. That's the smallest component, okay? And so if we're going from mole to representative particle, that means I need to remember that 1 mole of anything is equal to 6 times 10 to the 23rd. Now, how do you know if it's an atom? Well, ladies and gentlemen, an atom would be something like Na or Cu or Fe. An ion would be things like O, -2, Na plus, or something like F minus. A molecule would be something like CO2 or H2O, things that are bound covalently. Formula units would be things like NaCl, things such as CaF2, things that are bonded ionically. So it's how they're bonded or what they're made of that determines whether it's an atom, an ion, a formula unit, or a molecule. Okay, so let's take a look at our next example here. All right. In our next example, it says if you have 6 moles of sodium chloride, man, I'm really focusing on sodium chloride, how many representative particles would be present? So let's take a look back here. We're given 6 moles. And the idea is that we need to figure out how many representative particles. Well, in 1 mole of anything, there's 6 times 10 to the 23rd. Okay. So let's take a look. We're going to start with what's given. So we have 6 moles. Whoops. I'm screwing this up. There we go. We have 6 moles of NaCl. Now, remember, 1 mole of NaCl, that would be 6 times 10 to the 23rd. Now, what is NaCl? Is it an atom? Is it an ion? Is it a molecule, or is it a formula unit? It can't be an atom because it consists of more than one type of element. It can't be an ion because it doesn't have a charge. It can't be a molecule because it contains a metal. So it must be a formula unit of NaCl. So in 1 mole of NaCl, there are 6 times 10 to the 23rd, and this would be formula units of NaCl. You're going to say, well, how do I do this math? It's got this giant times 10 to the 23rd. Let me show you the quick and easy way to do this math particular problem, okay? So, ignoring the times 10 to the 23rd for now, okay? We're going to ignore that. I would like you to multiply 6 times 6. So I'm hoping you recognize that that is 36. Now tack on the times 10 to the 23rd, formula units of NaCl. Now I will tell you right now, technically correct, but math teachers across the world would be just cringing right now going, this is not appropriate scientific notation. In scientific notation, there can only be one number in front of the decimal place. So if there is assumed to be a decimal next to the 6, the idea is that we want to move the decimal place between the 3 and the 6, which means I'm going to take a factor of 10 out of this number and put it into the exponent instead, which means this becomes 3.6 times 10 to the 24th, and this would be formula units of NaCl. And that's how we solve for moles to representative particles. Okay. Now we're going to do the opposite, converting from representative particles to moles. Okay, literally doing the opposite thing. Same concept. The only difference is we're going from a representative particle to a mole in the center. Yellow, not my best color for this picture, okay? So again, we've got to remember, ladies and gentlemen, that 1 mole of anything is equal to 6 times 10 to the 23rd. Okay? That's what we got to remember. So let's take a look at our next question here. It says, if you have 1.2 times 10 to the 24th formula units of sodium chloride, how many moles would be present? So again, taking a look back, looking at our mole map, we're going from representative particle to mole. We're doing the opposite. Same similar setup, just the opposite direction. So we're going to start with what was given, which is 1.2 times 10 to the 24th formula units of NaCl. Now, why is it a formula unit again? Because sodium chloride is an ionic compound, and that's what a formula unit is, okay? If this had been nonmetals bonded together, we would call it a molecule. If this was just sodium as it is, it would be an atom. If this was Cl negative, we would call this an ion. But this is sodium chloride, so we call it a formula unit. Now, remember, 1 mole of NaCl is equal to 6 times 10 to the 23rd, and that is formula units of NaCl. Okay, so according to this, again, we're going to put this over 1. Okay, we're going to put the unit that we want to get rid of down in the numerator, or sorry, the denominator, formula units of NaCl, and we're going to put the unit we want, which is moles of NaCl at the top. 1 mole goes here. The 6 times 10 to the 23rd goes down here. And again, you're going to look at it and go, oh my gosh, these numbers are crazy. I've never dealt with the times 10 powers. Okay, so we're going to make it easier. If we were to do this mathematically, the easiest way is to make it so we have the same exponential focus on the times 10. So here's what we're going to do. We're going to take a factor of 10 out of here and put it here. So this is going to be 23, and now this becomes 12. I took a factor of 10 and moved it here. So what is 12 divided by 6? 2. The times 10 to the 23s are actually going to, guess what, ladies and gentlemen, cancel out. Just like the formula units of sodium chloride are going to cancel out, so we'll be left with our answer as 2 moles of NaCl. This literally is the opposite of what we just did in the previous question. So here is the hardest questions I can give you. These last two are the hard ones. And here's the reason why they're hard. We're going from mass to representative particle. You're like, what? What do you mean by mass to representative particle? Meaning, I am going to go from here, mass, to mole, then to representative particle. Notice, there is no way to go directly. So, got to go through the mole first. That's the key. You got to go through the mole first. So let's go ahead and work this out. All right. So in this particular question, we are starting with 232 grams of sodium chloride. Okay, 232 grams of sodium chloride. Our first thing we have to do is we got to convert the grams of sodium chloride into moles of sodium chloride. That is our first thing, which means we need, ladies and gentlemen, according to our little mole map, I need the molar mass, which we've already calculated before. The molar mass, ladies and gentlemen, of sodium chloride was 58 grams of sodium chloride for every 1 mole of sodium chloride. I put the grams down here for sodium chloride because I want them to cancel out. So I'm going to put the 58 grams here and 1 mole here. Okay. If we do this correctly, this would come out to be 4 moles of NaCl. The grams of sodium chloride cancel out. But I don't want the answer in moles. I want the answer in representative particles. So what representative particle is sodium chloride? If you said formula unit, you are correct. And that's what we're going to do. So we have to not do just one step. We actually have to do 2 steps. Okay, we're combining 2 steps. So we're going to take our answer from here. are 4 moles of NaCl. Now remember, 1 mole of anything, especially NaCl, is equal to 6 times 10 to the 23rd formula units of NaCl. So, again, we're assuming this is over 1. Moles of sodium chloride are going to go down here in the bottom. Formula units of sodium chloride are going to go in the numerator. For every 1 mole of sodium chloride, there are 6 times 10 to the 23rd formula units. So when we do the math here, again, the moles of sodium chloride are going to cancel out. They're gone. Goodbye. See you later. To do the math more easily, we're going to take 4 times 6, which would be 24. And then we're going to tack on the times 10 to the 23rd power. Okay. Now again, improper scientific notation. So what we're going to do is we're going to take a factor of 10 out of this number and put it into the exponent to make it 2.4 times 10 to the 24th. And therefore, this would be 2.4 times 10 to the 24th formula units of NaCl. That's the hardest problem I can get you, and all it is, it's 2 steps. But the idea, ladies and gentlemen, again, make sure you use that mole map to help you guide you through the process. Okay? Now, last one, promise you, last one. Converting representative particles to grams. We're literally going the opposite direction. So what we're going to do is we're going to go from here, representative particles, to mole, then to mass. So again, how many equations are we going to use? 2 equations. Okay? So in this particular problem, we're starting with 3.0 times 10 to the 24th, and this is formula units of NaCl. Okay? First thing first, got to remember, we are, ladies and gentlemen, going from representative particle to mole, which means 1 mole of anything is equal to 6 times 10 to the 23rd. That's what we need to have. So 1 mole of NaCl is equal to 6 times 10 to the 23rd formula units of NaCl. So formula units go down here in the denominator so that they cancel out, and mole goes into the numerator, and that's moles of NaCl. We're going to put the 6 times 10 to the 23rd formula units down here in the bottom, and the 1 mole up at the top. So again, mathematically, let's work this out here, okay? I want to make it so the exponents are the same. The easiest way to do this would be to take a factor of 10 out of this and put it into the 3.0, which would make this now 30, and this is going to be to the 23rd. So 30 divided by 6 would be 5. So this would end up being, ladies and gentlemen, because the times 10 to the 23s will cancel out, 5 moles of sodium chloride. Now, we're not done yet, because it's asking how many grams. We're at mole. We are, ladies and gentlemen, right here in the mole map, which means we need to get and figure out the molar mass, which we've already done, okay, of sodium chloride, which is found on the periodic table of elements. Okay, so we're going to take our value here, our 5 moles of NaCl, and again, we need to use our molar mass of sodium chloride, which, by the way, we have already used a number of times. There are 58 grams of sodium chloride for every 1 mole of sodium chloride. So moles of sodium chloride go down here in the bottom. Grams of sodium chloride go up here at the top. 1 mole of sodium chloride for every 58 grams of sodium chloride. Okay, so we'll end up with our answer in grams of sodium chloride. So if I do this right, 425, is that 290 grams of sodium chloride? Let's see, 540, carry the, yeah, 290 grams of sodium chloride is what we would have as our final answer. Okay, I know it was a lot, folks, but I'm hoping you can stop it, slow it down, think about it, what we just did, so that you can learn how to do these calculations and make sure you practice. Okay? There's practice, which always makes it a lot easier for you.